Hello everyone. Welcome back to our calculus course based on Thomas calculus. In our previous lessons, we learned what a function is, how to compose two functions, and how functions can model many real-world situations. Today, we will study another very important idea, inverse functions. Sometimes a function transports an input into an output, but later we need to reverse that process and recover the original input. Suppose a function takes an input x and produces an output y. If this function has an inverse, then the inverse function reverses this process. In other words, if the function sent a to b, then inverse function sent b back to a. We write the inverse function as f minus 1 of x. Notice that the symbol minus 1 does not mean raising the function to the power of -1. It is simply the notation used to represent the inverse function. For example, suppose you know the temperature in degree Fahrenheit and you want to find the corresponding temperature in degree Celsius. Or imagine that you know the final balance of a bank account and want to determine the original amount before interest was added. In both situations, we are trying to undo the work of a function. That is exactly what inverse functions do. They inverse the action of a function and take us back to the original input. Inverse functions appear throughout mathematics, science, engineering, computer science, economics, and many other fields. They will also become essential when we study exponential, logarithmic, and trigonometric function later in this course. Let's begin by learning their definition. An inverse function satisfies two very important properties. If we first apply the function and then apply its inverse, we obtain the original input. Likewise, if we first apply the inverse and then the original function, we again obtain the original input. These two relationships show that the two functions completely undo each other's work. There is also a beautiful geometric relationship between a function and its inverse. Their graphs are reflection of one another across the line y equal to x. Every point on the graph of the original function changed place with its coordinates reversed on the graph of the inverse function. For example, if the point a and b lies on the graph of the function, then the point b and a lies on the graph of its inverse. This symmetry makes it much easier to recognize inverse functions graphically. Now let's find the inverse of a simple linear function. The first step is to replace the notation f of x with the variable y. Then solve the resulting equation for x. Next, interchange the variable x and y. This step represents reversing the rules of the input and the output. The final expression for y becomes the inverse function. Finding an inverse is only part of the solution. we should always verify our answer. To do this, substitute the inverse function into the original function. If this result simplifies to x, then the first composition is correct. Next, substitute the original function into the inverse function. If this composition also simplifies to x, then we know that the inverse has been found correctly. Whenever both compositions return to original variable, we have successfully found the inverse function. An important question is whether every function has an inverse. The answer is no. A one-to-one function, also called an injective function, is a mapping where each element in the domain corresponds to a unique element in the codomain, and no two different inputs produce the same output. Mathematically, a function f from a to b is one-to-one if f of a equal to f of b implies a equal to b. A function has an inverse if and only if it is one-to-one. Consider the function f of x equals x squared. Different inputs such as 2 and negative 2 produce exactly the same output. Since one output corresponds to more than one input, we cannot uniquely reverse the process. For this reason, the function does not have an inverse function over all real numbers. To determine whether a function is one-to-one function or has an inverse, we use the horizontal line test. If every horizontal line intersects the graph at most once, then the function is one-to-one and an inverse function exists. Even when a function is not one-to-one, we can sometimes make it one-to-one by restricting its domain. Consider the function x squared. Over all real numbers, it does not have an inverse because each positive output comes from two different inputs. However, if we restrict the domain to non-negative value of x, then every output corresponds to exactly one input. Now the function becomes to one-to-one, and its inverse is the square root function. Domain restriction is an important idea because it allows many familiar functions to have inverses. Later in this course, we will use this idea again when studying trigonometric functions. Now consider the function f of x equals x cubed. Why the function is one-to-one and has an inverse? If you look at the curve for the function, you can use the horizontal line test. Imagine drawing a flat horizontal line anywhere across this graph. That line will only ever cross the blue curve exactly one time. This tells us that every single output y comes from only a unique input x. Because of this strict one-to-one relationship, the function has an inverse. To create an inverse function, we swap our input and outputs. For example, the point 2 and 8 on the blue curve becomes the point 8 and 2 on the red curve. When you swap all the x and y coordinates like this, it creates a mirror image. Geometrically, this means the red inverse graph cube root function is a perfect reflection of the original blue graph across the diagonal line y equal to x, be shown as the purple dashed line. This gives the inverse function, which is the cube root function. Before finishing, let's mention 3 common mistakes. The first mistake is thinking that an inverse function is the same as the reciprocal of a function. These are completely different concepts. The second mistake is forgetting to interchange the variable before solving for the inverse. The third mistake is ignoring the domain of the function. Without the proper domain, the inverse may not exist and may fail to be a function. Today we learn what inverse functions are, how to find them, how to verify them, how to recognize them graphically, how to use the horizontal line test, and why restricting the domain is sometimes necessary. In the next lesson, we will begin our study of exponential functions, one of the most important families of functions in calculus and many areas of science and engineering. Thank you very much for watching. If you find this video helpful, please give it a like, share it with your friends, and subscribe to the channel. Until next time, keep thinking mathematically.